Exploring Life. Chapter 2, Fundamentals of Atoms. Part 2. The periodic table is a systematic way of organizing elements based on their atomic structure. It's one of the most powerful tools in science, helping us understand the properties of matter and even guiding new discoveries. The table includes 92 naturally occurring elements, along with several heavier, unstable ones created in laboratories. And there's a legend behind its origin. Russian scientist Dmitry Mendeleev saw the arrangement of elements in a dream, and when he woke up, he wrote it down. Talk about good dreams. The periodic table is packed with useful information. Each element is listed with its atomic number, which tells us the number of protons, and its atomic symbol, usually 1 or 2 letters. The elements are arranged in order of increasing atomic number, and this organization reveals repeating patterns in their chemical properties. These patterns help us predict how elements will behave. The table is also divided into columns, or groups, where elements share similar traits. Some versions of periodic table even include atomic weights and common names for certain elements, making it a one-stop shop for understanding the building blocks of matter. This slide shows a periodic table, probably similar to the one hanging in your classroom. Take a moment to look closely. Can you spot the atomic symbols, the rows, called periods, the columns, called groups, and all the other information packed into each box? Can you find the iron? It's more than just a chart, it's a powerful tool for understanding the differences in atomic structure among the various atoms that make up everything around you. And that's exactly why this scientific illustration is so well known. It helps make the invisible world of atoms visible, organized, and easier to understand. But before we dive in, take a moment to appreciate something remarkable. The periodic table was created before scientists knew anything about protons, neutrons, or electron shells. That's the genius of the periodic table. Periods in the periodic table are the horizontal rows, and they represent different electron energy levels, or shells. The first row contains just 2 elements, hydrogen and helium, because their electrons only fill the very first shell, which holds a maximum of 2. As you move down the table, each new row adds another energy level. Most of the following rows can hold up to 8 elements, showing how electrons fill the next available shells. So, each period tells us something important about how an element's electrons are arranged. Remember the chair analogy from a few slides ago? Well, now you're looking right at those rows of chairs, lined up on the periodic table. Groups in the periodic table are the vertical columns, and they tell us the number of valence electrons each element has. As you move down in the table, atoms gain more energy shells, which makes them physically larger. But with each added shell, the outer electrons are farther from the nucleus, and the atom's ability to attract new electrons gets weaker. That's why elements lower in a group are generally less effective at forming strong chemical bonds. This is also why most biologically important elements are found in the first 3 rows of the periodic table. Elements within the same group have the same number of valence electrons, the electrons in the outermost shell of an atom, which is why they display similar chemical properties. Whether an element's valence shell is full, or nearly empty plays a big role in how it behaves, especially in chemical reactions and bonding. So by understanding groups, we can predict how different elements will interact with each other. The periodic table helps us understand how elements behave based on their valence electrons. Inert gases, also known as noble gases, are found in the far right column. Their outermost electron shells are completely full, which makes them very stable and unreactive as individual atoms. They're basically the introverts of the periodic table, content on their own, no need to mingle. In contrast, reactive elements, like those on the far left or near the middle, have incomplete valence shells and constantly strive for attention. They're eager to gain, lose, or share electrons in order to complete their shells. That need drives most of the chemical reactions happening all around us. Atoms are normally electrically neutral, meaning they have the same number of protons and electrons, so their positive and negative charges cancel out. But when an atom gains or loses electrons, it becomes an ion. If it loses electrons, it forms a cation, which has a positive charge, like sodium or calcium. If it gains electrons, it becomes an anion, with a negative charge, like chloride. These charged particles are essential in biology. They help send nerve signals, trigger muscle contractions, and keep fluids balanced in and around our cells. In short, ions may be small, but their impact is electric. Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. This means they share the same chemical properties, but they may have different physical properties, such as mass or stability. Some isotopes are stable, meaning their nuclei stay intact over time. Others are radioisotopes, which have unstable nuclei that break down, or decay, over time, releasing energy in the process. Look at the slide. It's all hydrogen, but not all hydrogen atoms are the same. There are 3 isotopes of hydrogen. They all have 1 proton, of course, but the number of neutrons is different. The first one is called protium. It has 1 proton and no neutrons. Protium is the most common form of hydrogen in nature. Deuterium has 1 neutron, and tritium has 2. The last 2 are heavier, and tritium is radioactive. Isotopes, and especially radioisotopes, have many important uses. Most people think of them in the context of energy production or the military, but they're also widely used in medicine for both diagnosis and treatment. One common imaging method is the PET scan, which stands for positron emission tomography. In this technique, radioisotopes like F18, C11, and O15 are attached to chemicals that the body naturally uses, like glucose. These compounds are then injected into the body, and doctors can trace how they move and where they collect, giving detailed images of how organs and tissues are functioning. In radiation therapy, other radioisotopes are used to destroy cancer cells while minimizing damage to healthy tissue. Isotopes also help us understand the past. Uranium-238 is used to date rocks, and carbon-14 is used to date various objects, including biological materials, and learn about the Earth history. So we'll explore how radiocarbon dating works. When introducing atomic structure, especially isotopes and ions, there's a standard shorthand format that shows the key information at a glance, without lengthy descriptions. On the left, we see carbon as it appears on the periodic table, symbol C, atomic number 6, and average atomic mass 12.01. On the right is carbon-13, an isotope of carbon. It has the same number of protons, but 1 extra neutron in the nucleus. This version also has fewer electrons than protons, giving it a 4+ charge. So, it's both an isotope due to the different number of neutrons, and an ion due to the charge imbalance. In this chapter, we explored atoms, the tiny building blocks of everything in the universe, including us. Born in the Big Bang and reshaped in stars and supernovae, they connect us to the cosmos. Protons, neutrons, and electrons give each element its identity, while isotopes and ions add diversity. Understanding atoms is more than memorizing parts, it's realizing that every breath, heartbeat, and drop of water depends on their interactions. Next, we'll see these atoms in action, bonding to form the molecules that make life possible. Now, take a moment to check if you've grasped the major points from this lecture. If anything's still unclear, don't worry, just go back and review the slides or your notes. A quick refresh can make all the difference. After understanding the basics of atomic structure, you're ready to explore how atoms come together to form molecules, which is where chemistry really starts to come alive.